All right, today we're going to do 7.4 trig substitution. If you turn your books, you might want to pause to find this in book to page 506. It's going to give you the integrals that we're going to want to use trig substitution for. Basically, if you have a radical and you don't know how to integrate it, this is a good technique. If you have a constant squared minus a function squared, we're going to use sine. If we have a constant squared plus a function squared, we're going to use tangent. And if we have the function squared minus the constant squared, we're going to use secant. Probably easier just to jump in to an example to show you what I'm talking about. So example I'm going to look at is dx over x squared times square root of 9 minus x squared. Now, one of the issues is you're tempted to say this looks like an inverse trigonometry one because of that part there, inverse sine in particular. But that x squared is what's going to confound it. And using u substitution directly, we're going to struggle with what to do with that x squared. So we can use this technique, and this is end up going to be this part of it, because this is a constant squared, 9 is the constant, minus a function squared, and the function's just x. So I'm going to take that function, x, and I'm going to set it equal to a sine theta, or a in this case is 3 sine theta. So that's how I make my decision about what to set up. Let's do a little bit of work before we jump into this. Let's find the derivative of this. So dx is equal to 3 cosine theta d theta. You know, I might as well go ahead and find what x squared would be too, because that's going to come up. Square both sides. X squared is equal to 9 sine squared theta. All right, that's going to give me enough for my substitution, so let's substitute in and see what we have. dx is now 3 cosine theta d theta. X squared we know to be 9 sine squared theta, times the square root of 9 minus x squared again, 9 sine squared theta. 3/9 can come out to the outside as 1/3. The integral of, let's just simplify where we can, cosine theta d theta over. Looks like now we have sine squared theta times square root of, I'm going to factor out this 9 and make this 1 minus sine squared theta. Simplifying some more, we're going to have cosine theta d theta over sine squared theta. The square root of 9 is simply 3, so that 3 on bottom can come out to the outside, over the square root of 1 minus sine squared theta. So all I really did is took care of that 9 there. I said the square root of 9 is 3, but since it's on bottom, it went out as 3. All right, rewrite this. 1/9 square root of cosine theta over sine squared theta. Square root of 1 minus sine squared using the Pythagorean identity is cosine squared theta. So that's equal to 1/9 cosine theta over, integral d theta over sine squared theta. Now square root of cosine squared theta is just cosine theta. Hopefully you can see that the cosine thetas cancel out, and it's going to leave me with, I'm going to write it over here to the left, 1/9 the integral of d theta over sine squared theta, which I will now write as 1/9 the integral of cosecant squared theta d theta. Well, this one's real straightforward to integrate now. So we know that the integration, because the derivative of cotangent is negative cosecant squared, we know the integration of cosecant squared is negative cotangent theta plus some c. It would be nice if we're done, but we're not quite done, because I now have it in terms of theta when I need it in terms of x. So this is the trick here. we're going to remember our original substitution. If you remember, the original substitution was x is equal to 3 sine theta. And to be able to put this back in terms of x, I'm going to have to draw a triangle. And I want to look at it from theta's perspective. In particular, let's talk about the sine theta. If I divide both sides by 3, I get sine theta is equal to x over 3. So from theta, we know that the sine is opposite of our hypotenuse. So if the sine of theta is x over 3, then this would be x and this would be 3. I'm going to go ahead and use the Pythagorean theorem to figure out this adjacent side here, which is 9 minus x squared. Now let's look back up at this original one and see what we have. Negative 1/9 times the cotangent of theta plus c. If I look at from theta's perspective, I want to talk about the cotangent. Cotangent is cosine over sine, or adjacent over opposite. So it's square root of 9 minus x squared over x. And now finally, we've integrated it by using trig substitution. All right, let's look at another problem. Dx over 4x squared plus 1. Well, this time I have a constant squared plus a function squared. If I have a constant squared plus a function squared, I'm going to use tangent. So to do this one, I'm going to let x, in this case, I'm sorry, the function is 2x. That's what's being squared. So I'm going to let 2x equal to it. So whatever that function is, equal to a, which is 1, times tangent a, or tangent theta. So our a is 1, tangent theta. So 2x equals tangent theta. Well, let's do some preliminary work. If we know that x is equal to 1/2 tangent theta, then dx is equal to 1/2. The derivative of tangent is secant squared theta d theta. And let's go ahead and square it. 4x squared is going to be tangent squared theta. Let's substitute it in everything we know. We know dx is equal to 1/2 secant squared theta d theta over the square root of, we know that 4x squared is simply tangent squared theta plus 1. Simplifying, we know that 1/2 secant squared theta d theta over square root of, using the Pythagorean identity, we know that that should be secant squared. Simplifying, we know that that's 1/2 secant squared theta d theta over the square root of secant squared theta is secant theta is 1/2. Well, one of these secant thetas cancel out, leaves me a secant theta d theta. That is one of our memorized formulas. The integration of secant theta is natural log of the absolute value of secant theta plus tangent theta plus c. That's theta. Okay, it'd be nice if we're done, but of course we're not done because it's all in terms of theta. So once again, we want to turn this into an x. So think back of our original substitution. We said let 2x equals tangent theta. In other words, 2x over 1. When I draw my triangle from the theta's perspective, tangent is opposite over adjacent, 2x over 1. Using the Pythagorean theorem, that is 4x squared plus 1 for the hypotenuse. Okay, go back to this one now, and we're going to say 1/2 natural log of secant. From theta's perspective, secant is 1 over cosine. So it is hypotenuse over adjacent, or square root of 4x squared plus 1 over 1, but we don't have to put the 1. Plus tangent, by original definition, is simply 2x. And I've now converted it to x's, and I've integrated it. All right, so we've seen examples of sine and tangent, so guess what? We're going to use one that is secant now. How do I know it's secant? It's a function squared minus a constant. And here we go, we have a function squared minus a constant will be that one. So I'm going to set my function there as x, and now I'm using a, which is the square root of that number, so it's radical 3 secant theta. Dx is equal to, that multiplier radical 3, the derivative of secant is secant theta tangent theta d theta. And let's go ahead and square this. X squared would be 3 secant squared theta. Substituting in everything we know. This is the square root of x squared, which is 3 secant squared theta minus 3. I just substituted x squared for 3 secant squared theta for x squared, over x, which is square root of 3 secant theta, times dx, which is square root of 3 secant theta tangent theta d theta. Looks much simpler now, doesn't it? Well, let's try to simplify and see what we can do. If I factor a 3 out under that radical, it's radical 3 parentheses secant squared theta minus 1. You should recognize that that is eventually going to be our Pythagorean identity to turn that into a tangent square. Times that radical 3, let's just pull that radical 3 out as a multiplier right now. Secant theta, tangent theta, d theta. I'm going to simplify a little bit. I hope you can see that this is a radical 3, cancels out with that radical 3. We have a secant theta on top, secant theta there. So now, what do I have? I have radical 3 integral. The square root of secant squared minus 1 is tangent squared theta. Nothing's left on bottom, times tangent theta d theta, which is radical 3 integral of, the square root of tangent squared is simply tangent. And tangent times tangent is tangent squared, theta d theta. Well, we saw this on Bellwork the other day, that my trick to this one is to use the Pythagorean identity, and then for tangent squared, I'm going to put 1 minus secant squared theta, because that's going to be radical 3. Integrating 1 is just theta, minus the integration of secant squared is tangent, so tangent theta, oops, let's back up a little bit. This is the identity is backwards. This is secant squared theta minus 1, not that one. So, sorry about that. So when I integrate this, the integration of secant squared theta is just tangent theta, minus the integration of 1 is just theta. Well, once again, we're almost there, plus c, obviously, but I have it in terms of theta, not x. So guess what? We need to draw our triangle. So, from the theta's perspective, if you remember back to what we originally said that x equals, we said that x equal radical 3 secant theta. In other words, secant theta is x over radical 3. Now, secant is hypotenuse over adjacent. So it's x there over the adjacent radical 3. Using the Pythagorean identity, or theorem, you get x squared minus 3. All right, so substitute it in. We have radical 3 times tangent theta is opposite over adjacent, so opposite is x squared minus 3 under the radical over square root of 3 minus theta. Well, we don't have a good one for theta, but I'm going to go from here to solve for theta. So if to solve for theta, you take the inverse secant of both sides, and I have a solution for theta. So this is arc secant, if you want to write it that way, either way, it doesn't matter, x over radical 3 plus c. And now we've integrated it. I know that's a lot to process. Hopefully, if you need, you can rewind this video and look through and do it a little slower. These are examples out of the book, so you can compare them to the book's solutions and look at the book for a few more. I'll be back in a little bit to help you out. Thank you.